Welcome to Bedtime Science. Did you know that deep in the rainforests of Central America, an ancient civilization independently invented the concept of zero, centuries before it appeared in Europe? Tonight we explore the quiet genius of the ancient Maya, their cities hidden beneath jungle canopy, their mathematics carved in stone, and their deep knowledge of the sky. In the next moments, we will gently move through how the Maya counted using fingers and toes, how they fed millions from the rainforest floor, how they mapped the stars without telescopes, how they built cities connected by stone highways, and what the jungle slowly reclaimed when those cities fell silent. Before we begin, if you find comfort here tonight, stay tuned for more from Bedtime Science. Now let's begin. The Maya built one of the most elegant number systems in human history. They counted in 20s, and the reason is disarmingly simple. They counted all 20 digits on the human body, 10 fingers, 10 toes. One complete person equaled one complete cycle of 20. Think about that for a moment. Your body right now holds a full set of Maya numerals. What's striking is how little they needed to write any number at all. The entire system rests on just three symbols. A single dot represents 1, a horizontal bar represents 5, and a shell-shaped glyph, sometimes drawn as a conch, sometimes as a stylized flower called nick, represents 0. With those marks alone, a Maya scribe could express any number imaginable. Unlike our system, which runs left to right across a page, the Maya wrote their numbers vertically. They stacked values in ascending powers of 20. The lowest position holds units from 0 to 19. The next position up holds multiples of 20. Above that, multiples of 400. A single dot placed in the third position, with shell glyphs below it, means exactly 400. Here's what made the Maya system genuinely rare. That shell glyph wasn't just a placeholder. It wasn't just a gap marker the way a space might hold a column in an accounting ledger. The Maya treated 0 as a complete digit, a quantity in its own right, which allowed arithmetic operations that would be impossible to notate cleanly without it. Most civilizations never made that conceptual leap. The oldest confirmed 0 symbol in Mesoamerica dates to 31 BCE. Archaeologists found it on Stela Sea at the Olmec site of Tres Zapotes, in what is now Veracruz, Mexico. The Maya may have inherited the concept from the Olmec, or they may have arrived at it independently. Either way, they developed it further than any other culture in the Western Hemisphere. In Maya writing, the 0 symbol takes more than one visual form. The conch shell version was first identified in 1880 by a German scholar named Ernst Furstemann, who was studying a pre-Columbian codex housed in Dresden. A second form, a flower glyph called nick, appeared on stone monuments and was identified by epigraphers in the 1960s. Two faces of the same idea, separated by almost a century of quiet research. The Maya put this number system to work on something much larger than counting. They used it to build a calendar that could reach across thousands of years. It's called the long count, and it too is written in their base 20 notation, with one important twist. In the long count, the third positional unit doesn't count 400. Instead, it counts 360, because 18 times 20 gives a closer approximation to the length of a solar year. From that point upward, the system returns to pure base 20. The next unit counts 7,200 days. The one above that counts 144,000 days. Each of these positional units has a name. A kin is 1 day. A winnow is 20 days. A ton is 360 days. A katon is 7,200 days, roughly 20 years. And a bakton is 144,000 days, roughly 394 years. These units allowed the Maya to span their recorded history across time scales that most ancient civilizations couldn't even name, let alone measure. The current long count cycle began on what Western calendars identify as August 11, 3114 BCE. In Maya terms, this date is called 4 Ajo 8 Kumku. It marks the mythological creation date, when the sky was raised from a primordial sea and 3 stones were set at the center of the cosmos. Every long count date that followed counts forward from that moment, in days. Using this system, a Maya scribe could express any date from the mythological creation of the universe to millions of years in the future, without ambiguity, all with the same 3 symbols stacked in their proper positions. Maya scribes could perform multiplication and addition across these large units. Modern scholars have confirmed that they tracked multi-century astronomical cycles without error, using only their positional number system and careful sequential calculation. No computers, no printed tables, just dots, bars, shells, and patience. The vigesimal system proved especially well suited for astronomy. Many celestial cycles align neatly with multiples of 20. The 260-day sacred calendar, the 360-day approximate solar year, the 584-day Venus cycle, and the 405-month lunar table all interact in clean mathematical relationships within this system. The Maya recognized those relationships and used them. One mathematical achievement stands out for its quiet elegance. The number 37,960. This is the total length of the Venus table recorded in the Dresden Codex. It's exactly divisible by 584, the Venus cycle. It's exactly divisible by 365, the civil year. And it's exactly divisible by 260, the sacred calendar. No remainders in any case. The Maya found this resonance and encoded it deliberately into their records. The base 20 system also underlies the calendar round, a 52-year interlocking cycle of the 2 principal calendars. Because 260 and 365 share no common factors other than 5, their least common multiple is 18,980 days. That's exactly 52 solar years and exactly 73 sacred cycles. After 18,980 days, every unique combination of Tzolk'in day and Hab date has occurred exactly once before the whole pattern repeats. Can you imagine living inside a calendar where no 2 days in your entire lifetime share the same name? The intellectual achievement of independently inventing a positional number system with 0 remains one of the rarest cognitive feats in history. Outside Mesoamerica, it's confirmed to have occurred independently only in Babylonia, in a different form without a true 0, and in India, from which the concept eventually reached Europe. The Maya didn't receive it from any of those traditions. They arrived at it entirely on their own. Those first 15 observations describe the architecture of a number system. What comes next is different. It's about how the Maya turned sound into stone. The Maya writing system is one of only a handful of fully independent writing systems ever developed in human history. No other literate civilization taught them. They created it without outside influence. And it encodes a complete spoken language, not merely numerals, not merely pictorial symbols. It can express anything a human voice can say. Linguists classify Maya script as logosyllabic. It combines logograms, signs representing whole words, with syllabic signs that represent consonant-vowel sound pairs. If you're looking for a comparison, it resembles Japanese writing more than it resembles any alphabet. It mixes meaning signs and sound signs in a single flowing text. The system contains roughly 800 known signs. That number was actually the first clue that led to its decipherment. It was too many signs for a pure alphabet, too few for a purely logographic system like Chinese. The count implied something mixed, something in between. In 1952, a Soviet linguist named Yuri Norizov published a breakthrough article arguing that Maya glyphs were partly phonetic. He was working in Leningrad, using second-hand photographs of codex pages. He had never visited a Maya site. He had never walked through a jungle or touched a carved stela, and he was contradicting the prevailing academic consensus, which held that the glyphs were purely symbolic and couldn't be translated. Cold War politics delayed the acceptance of his work in Western academia for decades. But Norizov's insight was simple and powerful. When the Spanish bishop Diego de Landa recorded a so-called Maya alphabet in the 16th century, the Maya scribe who helped him had actually been writing syllables, not letters. When de Landa asked for the sound B, the scribe wrote the glyph for the syllable B. What looked like confusion was actually the key to the code. Norizov understood that. His method worked. He demonstrated that a consonant-vowel-consonant word could be written with two syllabic glyphs, where the final vowel of the second glyph is silent. Using the glyphs tsu and lu, he spelled out tzul, the Maya word for dog. This synharmony rule became a cornerstone of Maya decipherment. Acceptance came slowly. A conference in Albany, New York, in 1979 became a turning point, uniting Maya epigraphers under linguistic methods for the first time. David Kelly's 1976 publication, Deciphering the Maya Script, had already applied Norizov's phonetic approach to monumental stone inscriptions with some success. Today, scholars can read more than 90% of known Maya glyphs. The remaining opaque elements include rare ritual terms and some personal names. The full body of Maya inscriptions, spanning some 3,000 carved monuments, painted ceramics, and 4 surviving codices, now tells a coherent history. Dynasties, wars, marriages, celestial events, cosmological cycles, all of it readable. Only 4 codices survived: the Dresden, the Madrid, the Paris, and the Grolier. These are the only pre-Columbian Maya books that escaped the systematic burning ordered by Bishop Diego de Landa in 1562. And in a deep historical irony, Landa himself also preserved the only substantial record of the Maya syllabary, the very document that, centuries later, became the key to decipherment. The codices were made from the inner bark of wild fig trees, a material called hoon. Freshly cut branches were stripped of their outer bark. The inner bark was soaked in running water or boiled in lime water until the fibers softened. Then the strips were layered at right angles on a drying board and felted together by pounding with a grooved stone bark beater. Patient, physical, repetitive work. The resulting sheets, technically felted fiber rather than true paper, were coated with a white lime plaster. This gave the scribes a smooth, paintable surface. They worked with fine brushes of animal hair or plant fiber, painting in black, red, and occasionally blue, green, yellow, and orange pigments. The finished sheets were folded accordion style into screen-fold books, sometimes dozens of panels long. Wooden covers protected the fragile pages. The Dresden Codex, now preserved in Germany, unfolds to nearly 4 meters in length. Scribes, called aj-tsib, held high social rank. Papermaking and writing were considered sacred duties. The act of writing was itself a ceremonial act, closely tied to the divine. These weren't bureaucrats filling out forms. They were performing ritual. Maya glyphs were also carved into stone stelae, lintels, stairways, and architectural facades throughout the Maya world. These monumental inscriptions recorded dynastic histories, accessions, war victories, and celestial alignments. Stones served as permanent public record. The bark codices functioned more as astronomical almanacs and ritual calendars, portable, specialized, sacred. The total corpus of known Maya inscriptions makes this one of the best documented ancient civilizations in the Americas. Modern epigraphers continue to find new inscriptions at sites revealed by laser scanning. Computational methods are now being applied to assist in reading damaged or eroded texts. The decipherment continues. Those observations describe how the Maya encoded language into stone and bark. Now we look upward at how they read the sky. Maya astronomy was entirely naked eye. No telescopes, no optical instruments of any kind. Their precision came from generations of systematic observation, meticulous record-keeping, and a mathematical system powerful enough to track celestial cycles across centuries. They tracked Venus with extraordinary care. The actual synodic period of Venus, the time between successive appearances as the morning star, is 583.92 days. The Maya recorded it as 584 days. That approximation accumulates a total error of less than 2 hours over a full 500-year span. 2 hours in 5 centuries. And they didn't simply accept the rounding error. The Dresden Codex contains explicit correction tables. After 61 Venus cycles, Maya scribes subtracted 4 days from their running count. They repeated this correction 4 times. After 57 cycles, they subtracted 8 days. These corrections are mathematically equivalent to a modern decimal approximation of 583.92 days. This was sophisticated error correction, achieved without decimals. The Venus table in the Dresden Codex divides each 584-day cycle into 4 observable phases: 236 days as the morning star, 90 days of inferior conjunction invisibility, when Venus passes between Earth and the Sun and can't be seen, 250 days as the evening star, and 8 days of superior conjunction invisibility. Those 4 numbers sum to 584. This phase-by-phase breakdown reflects actual observational records, gathered over generations of patient watching. Scholars now believe the Venus table was developed at Chichen Itza during the Terminal Classic period, roughly 800 to 1000 CE. The Caracol at Chichen Itza stands as the most iconic surviving Maya astronomical observatory. Caracol means snail in Spanish, named for its internal spiral staircase. It was built around 906 CE and is one of the few circular structures the Maya ever constructed, deliberately contrasting with the rectangular architecture surrounding it. The Caracol rises roughly 75 feet in total height. It's built as 3 superimposed cylindrical structures, each with a progressively narrower diameter. Its windows and doorways are precisely aligned to track Venus's extreme northern and southern rising points, the spring equinox sunset, and other key celestial events. On the flat Yucatan Peninsula, with no natural hills or horizon markers, Such a structure was genuinely necessary. You can't mark a star's position against a featureless horizon. You need a frame. The Dresden Codex also contains an eclipse prediction table spanning 405 lunar months. That's 11,960 days. Recent scholarship has revealed something unexpected about this table. It wasn't originally designed to predict eclipses at all. It emerged from a lunar calendar whose 11,960-day length was chosen because it equals exactly 46 sacred 260-day cycles. 46 times 260 equals 11,960. The table harmonized lunar time and sacred time. The eclipse prediction power was a consequence, not the original intent. Maya daykeepers learned to use the table's 405-month cycle to anticipate when eclipses could occur, and they maintained its accuracy for over 700 years by using an elegant system of overlapping tables with periodic resets. The 260-day sacred calendar, the Tzolk'in, combined the numbers 1 through 13 with 20 named day signs. It cycled continuously, without reference to the solar year. Its origins remain debated. Some scholars suggest it may approximate the human gestation period. Others think it tracks the agricultural growing season at certain Maya latitudes, or the interval between the zenithal passages of the sun at specific highland sites. Nobody knows for certain. It's one of those questions that might never resolve completely. The 365-day civil calendar, the Hab, was composed of 18 named months of 20 days each, plus a final period of 5 nameless days called Wayeb. These 5 days were considered dangerous, inauspicious, a thin spot in time. The Hab didn't use a leap year correction, so it drifted slowly against the tropical solar year, about 1 day every 4 years. When the Tzolk'in and the Hab run simultaneously, they produce a unique combined date once every 18,980 days. That's a 52-year cycle called the calendar round. Within any human lifetime, no 2 days shared the same designation. The end of each 52-year cycle was marked by extinguishing all fires and drilling new ones, a ceremony of cosmic renewal. Every flame in every hearth put out, then relit from a single new spark. Maya astronomers tracked the Milky Way across the night sky. They interpreted its annual arc as the form of the cosmic saber tree, Yaksh, the axis connecting the upper world of sky gods, the middle world of living humans, and Xibalba, the deep underworld beneath. When the Milky Way stood vertical in the night sky, it was the world tree at its most upright. City planning reflected these observations. Many wells in Maya ruins functioned as zenith tube observatories, allowing astronomers to track the precise moment when the sun passed directly overhead. At the latitude of many Maya cities, this happens twice a year. It was used to calibrate the agricultural calendar, architecture serving astronomy, astronomy serving agriculture, agriculture serving everyone. No metal tools, no wheeled vehicles for transport, and yet Maya astronomers built some of the most accurate pre-telescope astronomical records in human history. The classic Maya, operating between roughly 250 and 900 CE, achieved a precision in celestial record-keeping that European astronomy wouldn't match until several centuries later. Those observations describe how the Maya read the sky. Now we look downward at the forest floor and how they fed entire cities from it. The milpa is often described, incorrectly, as slash-and-burn agriculture. It's not. The milpa is a sophisticated multi-decade rotational system. Forest clearings cycle through annual cropland, managed orchards and mature forest over a period of roughly 20 years before being cleared again. At any given moment, only about 20% of the managed terrain is in the open field stage. The rest is regenerating or mature forest. 80% of the land always looks like jungle, because it is jungle, managed jungle. The first stage lasts about 4 to 5 years. It begins with the selective clearing of a forest plot, roughly 1 hectare in size. Valuable trees are spared. Others are felled and allowed to dry. Then the dry material is burned in a carefully controlled fire. The burn adds a pulse of minerals and nutrients to the soil. It creates the open conditions needed for annual crops. The primary crops are the Mesoamerican quartet: maize, beans, squash, and chilies, cultivated together in a practice now recognized as one of the most efficient polycultures in the world. Each species occupies a different niche. Maize grows tall. Beans climb the maize stalks. Squash spreads along the ground. Each one supports the others. The partnership between beans and soil bacteria is ecologically critical. Bacteria of the genus Rhizobium colonize the bean roots and fix atmospheric nitrogen into a form the plants can use. Studies show that beans can acquire up to 60% of their nitrogen through this symbiotic fixation. In intercrop stands, this fixed nitrogen becomes available to neighboring maize plants, reducing the need for external fertilization on nitrogen-poor tropical soils. And the squash leaves perform their own quiet function. Spreading horizontally across the ground, they reduce soil temperature, retain moisture, suppress competing weeds, and cut erosion. The root architectures are complementary too. Maize roots are shallow and vertical. Bean roots go moderately deep. Squash roots explore the deepest soil layers. They don't compete for the same water. They cooperate without knowing it. In the second stage, beginning after the first few years and lasting until roughly year 12, farmers start encouraging woody trees and perennials among the annual crops. Quick-yielding species come first: banana, plantain, papaya. Then slower maturing fruit trees are added over time: avocado, guava, allspice, cherimoya, and the protein-rich ramon tree. Researchers have cataloged over 160 confirmed tree species that Maya farmers favor and manage within the Milpa cycle. Timber species, medicinal plants, fiber plants, food trees, all maintained by human intention even when the land appears, to an outside observer, to be unmanaged forest. By the third stage, roughly years 12 to 20, the canopy closes above the maturing fruit trees. The plot becomes a forest garden, visually indistinguishable from natural jungle, but rich in productive species selected and arranged by human decisions over generations. Shade-tolerant crops and medicinals grow beneath the canopy. You could walk through it and never realize someone planted it. The fourth stage marks the return of closed canopy forest. The root networks, mycorrhizal fungi, soil structure, and organic matter accumulated over the full 20-year rotation have restored the land's agricultural capacity. And here's the key: Maya forest gardeners traditionally maintain multiple milpa plots simultaneously, each at a different stage. The result is a permanent patchwork mosaic of productivity. Some plots growing maize, some growing fruit, some resting, all working. This system has sustained the population of the Yucatan Peninsula for more than 3,500 years. In 2022, the United Nations Food and Agriculture Organization designated the Peninsular Maya Milpa as a globally important agricultural heritage system, recognizing its role in preserving biodiversity and cultural identity simultaneously. Because at least 80% of any milpa terrain is always in some phase of regenerating or mature forest. The system maintains forest cover, wildlife corridors, and soil integrity far more effectively than conventional agriculture at comparable population densities. But feeding a city takes more than food. It takes water. The Maya constructed elaborate water storage systems to sustain their forest cities during the dry season. At Tikal, in Guatemala, archaeologists documented what's now recognized as the oldest water filtration system in the Western Hemisphere. The Corriental Reservoir, built roughly 2,185 years ago, used crystalline quartz and zeolite as a molecular sieve. Zeolite is a porous mineral that removes heavy metals, harmful microbes, and chemical pollutants from drinking water. The zeolite used at Tikal's Corriental Reservoir was sourced from a location miles away from the city, deliberately imported, deliberately placed. The same minerals are standard components of modern industrial water purification systems. We use the same trick today. The Maya figured it out 2,000 years earlier. The broader water infrastructure at Tikal included the largest ancient dam yet identified in the Maya area, a switching station for seasonally redirecting reservoir flows, a cofferdam built specifically to allow dredging of the largest reservoir, and the deepest rock-cut canal segment in the Maya lowlands. This wasn't improvised. It was a deliberately designed, continuously maintained urban water system. Research from the site of Ucayali in northern Guatemala has revealed that Maya water access mirrored social hierarchy. 3 reservoirs at the site served different social strata. The elite's monumental reservoir featured natural filtration through rock-filled inlet channels, shade-providing vegetation, and elevated placement for gravity-fed flow. The commoner's reservoir showed far greater biological contamination. Even clean water was stratified by class. Those observations describe how the Maya fed their cities and managed their water. What comes next was hidden under the forest canopy for 1,000 years and only recently made visible by pulses of laser light. For most of the 20th century, archaeologists believed the Maya lowland forests were home to scattered, isolated city-states separated by largely empty jungle. That picture was wrong. Beginning in 2015 and accelerating from 2018 onward, a technology called LIDAR, airborne laser scanning that strips away vegetation to reveal ground topography, overturned that model entirely. The PACUNAM LIDAR initiative, launched in 2016 as the largest single LIDAR survey in the history of Mesoamerican archaeology, scanned over 2,100 square kilometers of the Maya Biosphere Reserve in northern Guatemala. When the results were published in Science in 2018, led by researchers from Chilean University, they identified 61,480 ancient structures in the survey region. 61,000 structures, hidden under trees, and that was just the beginning. A follow-up study in 2025, using reprocessed LIDAR data across 95,000 square kilometers spanning Guatemala's Petén, western Belize, and Mexico's Campeche and Quintana Roo states, revised the late Classic Maya population estimate upward to between 9.5 and 16 million people. That's a lot of mouths to feed from a forest floor. A separate, highly focused LIDAR study of the Mirador-Calakmul karst basin in northern Guatemala, covering about 1,700 square kilometers, identified 964 archaeological settlements. Researchers condensed these into 417 ancient cities, towns, and villages, organized into at least 6 hierarchical tiers based on site area, construction volume, and architectural configurations. The largest sites tower above the canopy. The smallest are hamlet-scale clusters, barely visible even to LIDAR. And these cities weren't isolated. They were connected by 177 kilometers of elevated causeways. Stone roads built during the Middle and Late Preclassic periods, from roughly 600 BCE to 150 CE. That makes them one of the earliest large-scale engineered road networks in the Americas. They predate the rise of the classic Maya by centuries. The Maya called these roads Sakbiab, white roads. In Yucatec Maya, the word refers to the lime plaster surface that once covered them, white and reflective under the tropical sun. The causeways varied in scale. Intrasite roads within a single urban center measured between 9 and 40 meters in width. The elevated road from Tintal to El Mirador, still standing 5 to 7 meters above the jungle floor, reaches up to 40 meters wide at its broadest points. At its highest elevation, it rises as high as 20 meters above the surrounding canopy. Imagine a white stone highway, wider than a modern 4-lane road, running through tropical forest 2,000 years ago. They were engineered with stone retaining walls on both sides, filled internally with boulder aggregate, gravel, pebbles, and powdered limestone called saskab. The final surface was finished with a lime plaster cap. Sections of that plaster survive intact after 2,000 years, still white, still hard. And the Sakbiab weren't just for getting from one place to another. They served multiple purposes simultaneously: ceremonial procession routes, boundaries between social zones and ritual zones, components of regional water management. Elevated causeways directed rainfall runoff into reservoirs, terraces, and wetland agricultural systems. The roads were also water infrastructure. One structure, 4 functions. El Mirador, the great preclassic metropolis at the heart of the basin network, covers roughly 132 square kilometers of built urban terrain. Its western civic group holds an architectural volume exceeding 4 million cubic meters per square kilometer. In the preclassic period, before 150 CE, that density of construction was among the greatest on Earth, and it was all hidden under trees until LIDAR found it. The 2025 LIDAR study found a strikingly regular pattern across the Maya lowlands. Nearly every ancient residential structure was located within roughly 5 kilometers of a plaza complex. This uniform spacing implies a consistent, civilization-wide planning logic, not organic sprawl. Organized spatial relationships between civic centers and their dependent populations. The LIDAR data also revealed extensive raised agricultural terracing, irrigation canals, and wetland field systems covering large portions of the lowland terrain. These features, invisible from the ground under dense jungle, indicate a managed agricultural territory of far greater intensity than was previously imagined. Defensive earthworks appear too: ditches, berms, and walls surrounding many Maya cities and stretching along the causeway network. Their presence suggests that the terminal classic period was marked by significant conflict between city-states. Not peace, not constant war, something in between, shifting over decades. And the data reveals something else: a city-level integration between urban infrastructure and forest ecology. Shade trees were maintained around reservoirs to suppress cyanobacterial blooms in warmed water. Green corridors and managed forest plots appear between residential zones and agricultural terraces. Maya cities were not clearings in the forest. They were embedded within it. The city and the forest were the same thing, seen from different angles. The scale of what LIDAR has revealed is still being absorbed. As researcher Francisco Estradabelli of Chilean University put it, the findings show the classic Maya lowlands were not only densely inhabited, but also highly structured, with consistent patterns of urban and rural organization across an immense region. The Maya were not a collection of isolated ceremonial centers. They were something much bigger. Those observations describe what the forest was hiding. Now we move closer into daily life, the rituals, and the materials that shaped Maya experience. Cacao was the most powerful economic medium in the Maya world. Not gold, not silver, cacao beans. They functioned as commodity money, divisible, portable, universally desirable, and trusted across hundreds of miles of trade networks. They were stored in royal warehouses, regulated by the state, paid to soldiers, and used to settle debts across Mesoamerica. Cacao was consumed primarily as a hot liquid beverage, frothy and spiced, bitter, not sweet, served in ceramic vessels that have been found as far north as the American Southwest. The bean's use as currency began at least as early as the 7th century CE, becoming dominant by the 8th century. Colonial-era Spanish accounts recorded the prices. A turkey cost 20 beans. Smaller transactions required fewer still, and counterfeiting was a known economic crime. Some cacao beans were hollowed out and filled with clay or dirt to mimic the weight of genuine beans, an inflation problem that may have contributed to the currency's eventual decline. People have always been creative with money, and other people have always been creative about faking it. The ancient Maya ball game, known as pits in the classic lowlands, is one of the oldest continuously practiced sporting rituals in human history. Evidence goes back at least to 1650 BCE. More than 1,300 ball courts have been identified across Mesoamerica, from Arizona in the north to Nicaragua in the south. The ball was made from solid natural rubber, harvested from the Castilla elastica tree. In larger versions, it could weigh up to 4 kilograms, about 9 pounds. Players struck it using only their hips, thighs, and upper arms. The sport required substantial protective gear. Leather or wooden yokes worn around the waist, knee pads, wrist guards, and oversized animal headdresses. This was not a casual game. The court was shaped like an uppercase, a long central playing field with parallel enclosed ends. Elevated platforms along the sides allowed spectators. Stone rings mounted vertically on the side walls appeared during the post-classic period. Passing the ball through the ring, which was barely larger than the ball itself, ended the game on the spot. A rare feat, and celebrated loudly. The ball game carried deep cosmological meaning. It reenacted the journey of the hero twins into Xibalba, the underworld, as told in the Maya creation epic, the Popol Vuh. Major formal ball games were ritual performances, sometimes culminating in human sacrifice, depicted explicitly in carved murals at the Great Ball Court of Chichen Itza. Jade was, without question, the supreme prestige material of the Maya world, valued more highly than gold. The Aztec Emperor Moctezuma reportedly told Hernán Cortés that jade pieces he was sending to the King of Spain were worth more than 2 loads of gold each. Gold was pretty, jade was sacred. The Maya used exclusively jadeite, sodium aluminum silicate, not the softer nephrite jade common in East Asia. Jadeite is extremely hard, ranking 6.5 to 7 on the Mohs scale, and it forms only under specific high-temperature, low-pressure geological conditions associated with tectonic faults. The Motagua River Valley in Guatemala is one of only 6 known jadeite sources in the entire world. It was the principal source for Maya civilization. Jade's symbolic meaning ran deep. It represented the maize god, the deity of agricultural fertility and rebirth. It represented maize itself, whose green color it mirrors. It represented water and vegetation, and it represented what the Maya called Ik, the breath soul, one of several souls the Maya believed each person carried. Jade earspools were thought to be portals through which the breath soul could pass between worlds. When a person died, a jade bead was placed in their mouth, currency for the journey through the underworld. This practice echoes the Greek tradition of placing a coin in the mouth of the deceased for the Farum and Karen. Two civilizations, separated by oceans and centuries, arriving at the same ritual gesture. The Maya dead were also buried with maize in the mouth, a symbol of the maize god's resurrection cycle, the grain that falls into the earth and rises again. Maya burial practices reflected a deep belief in cyclical time. Kings and rulers were interred beneath the temples they had built. The temple became a symbolic mountain, a witz, above the royal tomb, and the tomb became a symbolic cave. The entry point to the underworld from which the king would eventually be reborn as a divine ancestor. The architecture of death mirrored the architecture of the cosmos. The ceiba tree, known as Yaxch in Yucatec Maya, was the sacred axis mundi, the world tree connecting earth, sky, and underworld. It's still planted at the center of Maya villages today as a living cosmological symbol. Its image appeared in painted murals, carved monuments, and ceramic art across the classic Maya world. And when the Milky Way stood vertical in the night sky, it was the ceiba, the world tree at its most upright. Maya polities were organized around the concept of the divine king, the Kayuhul Ajo, or Holy Lord. The king served as the living embodiment of the axis between human and divine. His ritual duties included bloodletting ceremonies, astronomical observations, agricultural calendar pronouncements, and public performances of mythological narratives. These were not merely symbolic. They were understood to maintain the ordered functioning of the cosmos itself. If the king stopped performing the rituals, the world might stop working. And all of this was achieved without metal tools, wheeled vehicles, or draft animals. The Maya built massive stone cities, engineered water systems, carved jade to fine detail using abrasive sand and string, and produced a written literature complex enough to record philosophical thought. The physical labor of their civilization ran entirely on human energy, organized through social structures that could direct tens of thousands of workers toward monumental engineering goals. Human hands, human backs, human patience. Those observations describe the texture of daily life and sacred practice. What comes last is the quietest part. What happened when the cities fell silent, and what remains? The classic Maya collapse was not a sudden event. It was not a true extinction. What archaeologists call the terminal classic collapse, spanning roughly 750 to 950 CE, was a gradual depopulation and political fragmentation of the southern Maya lowlands. The major stone cities of the Petén region were progressively abandoned, but Maya civilization itself continued. Communities in the northern Yucatan and Guatemalan highlands persisted, adapted, and in some cases grew stronger. A study published in Science Advances used oxygen isotope analysis from a stalagmite in a Yucatan cave called Grutas T. Zabna to reconstruct rainfall patterns at seasonal resolution for the years 871 to 1021 CE. This was the first time individual wet season and dry season rainfall conditions had been isolated for the terminal classic period. The stalagmite record revealed 8 wet season droughts lasting 3 or more years during this period. The longest was a single continuous drought of 13 years. 13 years without reliable rain. Think about what that means for a civilization that depends on stored rainwater and seasonal agriculture. Lead author Daniel James of University College London noted that what surprised the research team was how clearly the seasonal cycle was recorded, calling it highly unusual to access past climate information at such high resolution. Construction of monuments and political activity at major sites stopped at different times during this climate stress. The collapse was staggered, non-simultaneous. Different cities fell silent in different decades. Not a single catastrophe, but a slow unwinding. And drought wasn't the only pressure. Scholars have identified a cluster of reinforcing forces. Prolonged droughts reducing agricultural yields and drying surface water, intensifying warfare between competing city-states over diminishing resources, political fragmentation as dynastic legitimacy collapsed alongside harvests, disrupted trade routes, possible soil degradation from agricultural overextension. Each problem made the next one worse. The collapse was systemic, not singular. The northern Maya lowlands, less severely affected by the terminal classic droughts, experienced a period of political consolidation and architectural creativity, while the south was contracting. Cities like Chichen Itza grew in power and sophistication during the very period when Tikal and Kapan were declining. The Karakal Observatory was built in 906 CE, well into the terminal classic. The north was building while the south was emptying. When Spanish ships arrived in the 16th century, they didn't find ruins. They found living Maya societies, continuity across 1,000 years. Today, at least 30 distinct Mayan languages are spoken by roughly 6 million people across Guatemala, Mexico, Belize, El Salvador, and Honduras. Guatemala alone has formally recognized 21 Mayan languages. Between 40 and 60% of its total population speaks a Mayan language as a first or second tongue. Yucatec Maya, called simply Maya by its speakers, is spoken by approximately 800,000 people, the vast majority on the Yucatan Peninsula. That makes it the most spoken indigenous language of Mexico after Nahuatl. Its practical alphabet was only standardized in 1984, in a process that, for the first time, included native speakers, educators, and linguists working together. The Milpa agricultural cycle that fed classic Maya populations of up to 16 million continues to be practiced across the Yucatan today. Contemporary Maya farmers have begun integrating traditional Milpa knowledge with climate resilience research. The system's inherent biodiversity and soil management make it more resistant to the irregular rainfall patterns now intensifying. Modern archaeology and epigraphy have recovered the outlines of the classic Maya world, a political system of competing dynasties, elaborate diplomatic marriages, recorded histories spanning millennia, a cosmological framework so internally consistent and mathematically precise that it still rewards close study. The decipherment of Maya glyphs, substantially achieved within living memory in the latter decades of the 20th century, means that this civilization is now speaking to us directly, in its own words, for the first time in 500 years. We can read them now. That's new. That happened in your lifetime or your parents' lifetime. After centuries of silence, the glyphs are talking again. The long count calendar was designed not just to record the past. It projects time forward into cycles so large that no human civilization could outlast them. The current Bacton cycle stretches from 3114 BCE to a future completion point more than 1,000 years from now. A civilization that counted in 20s, that read the planets with naked eyes, that fed millions from a managed forest, all without metal tools or wheels. And somewhere tonight, the same stars the Maya tracked still cross the same sky above the same forests. Venus rises and sets on its 584-day rhythm. The Milky Way arcs overhead, the world tree turning slowly. Beneath the canopy, the stone causeways still run through the dark. White roads, dusted with lime, connecting cities that never entirely stopped being cities. The glyphs wait on their monuments, patient, readable now after centuries of silence. The calendar counts forward. And somewhere, in a village on the Yucatan Peninsula, a ceiba tree stands at the center of a plaza, its roots reaching down into the old stone, its branches reaching up toward the same sky that the astronomers of the Caracol once watched through narrow windows aligned to the path of Venus. The forest breathes. The numbers hold. The days continue.